Welcome to the Davos in the Desert podcast series. My name is Mark Oliver and I am the producer of the Davos in the Desert podcast series. Our podcasts feature thought leaders in business and public policy. Our sessions are meant to be informative and thought-provoking. The topic of this session is an overview of data center cooling technologies, and our guest is Nick Hume. Mr. Hume is the founder and managing director of Hume Consulting. Without further ado, here is David Wanatic, the CEO of Davos in the Desert and the host of our podcast series.
Hello, everyone. My name is David Wanatic. I'm the CEO of Davos in the Desert. Today, we have a very interesting session that will focus on data center cooling technologies. Here to speak about this issue is Nick Hume, who is the founder and managing director of Hume Consulting, which specializes in IT strategy, cloud and data center, sustainable AI infrastructure, process optimization, and compliance. Nick has had experience working as a chief technology officer at a U.S. startup. He's a former chief operating officer and group chief information officer at a European startup. And earlier in his career, he was the Microsoft Azure and leader at Amazon AWS. So Nick, thank you very much for joining us.
Thank you for having me, David. Pleasure to be here.
Great. So for those who don't know very much about data centers, maybe you can just say a few words about what data centers do, what happens at data centers, and then secondly, what are the growth drivers for data centers?
Yeah, so data centers are littered around the earth, and people might have stumbled past them in their driving on the freeways and highways around. Typically are unmarked. They're not something that a company wants to particularly bring a lot of attention to, given a data center is storing, managing, processing a lot of data. It's storing a ton of personal information. It's processing your email. It's serving medical data to hospitals. All kinds of different things are stored in the cloud and in data centers. So AWS, Azure, large hyperscale size, as much as colo providers that you can bring your own data and your own infrastructure into facilities and have those companies manage it for you. A lot of existing businesses would do these things on premise, so their data center would naturally be in their offices, a loud facility spinning lots of fans, processing their local file servers and email servers and things like that. So a data center is just an amalgamation of digital infrastructure and information pertaining to a business's the ability for businesses to run, operate, and some of these businesses run specifically as a result of these data centers. So they're hosting all their critical information services that they then go and sell on as a service themselves.
Okay, so data centers are basically where the cloud lives.
Essentially, yeah. I mean, the cloud is a nice version of a word for it. And yeah, that's a yeah.
Okay, so there's quite a lot of construction of data centers. Maybe you can talk about where data centers should be located. Are they typically in dense urban areas or more, further afield from city centers?
Yeah, I've failed to answer that last question. You talked about growth drivers. So what are those things really at the moment is AI. Everyone's talking about AI. The data center growth as a result of AI is exploded and exploding. The ability to sort of serve up these high demand needs for ChatGPT is sort of the everyone points at ChatGPT as the kind of the breaking moment, the watershed moment for AI and popularity. And it's really forcing a lot of new growth of data centers, existing growth in existing data centers, like brand new builds and retrofits of existing data centers. It's really challenging to go and build these things, given the power and the infrastructure needs and the supply needs to go do it. So there's a lot of innovation there. We can talk about that a little later. So really, like these data centers where they've been located, it's a good segue actually, because where they've been traditionally located, has been in, cheap land, cheap power, access to fiber, network connectivity. And so you'll see those kind of installations, and big businesses have gone and spent a lot of money to buy land and build these things. Typically, the Data Center Alley in Virginia, you'll see a bunch of data centers just up and down the north-south corridor of the fiber run. The counties and the municipalities allowing them and giving them tax incentives to do so brings a lot of business. It uses a lot of resources, adds a lot of jobs. So those have been some of the main components. Here in Washington State, if you go out to Eastern Washington in Quincy, data centers from Microsoft, for example, will be out there. They're close to hydropower. And so I'll just hang off the Columbia River, go down to Boardman, Oregon, same thing. A lot of Amazon data centers down there too. So, it's the unit economics of data centers has been, 3 or 4 main components. But increasingly, the proximity where those consolidation points have been these large scale, 100+ megawatt data centers, AI and other services are kind of bringing that data back closer to the user, lower latency requirements, repatriation of data, bringing that closer and back to sovereign data, land closer to customers and users, given regulatory kind of pressures and sensitivities around those things. So there's a lot of moving parts, and that's changing to what was traditionally deployed.
Mhm. And do companies that set up data centers, they take into account the risk of natural disasters like earthquakes and floods and things like that?
Absolutely. Yeah. So the large data centers, and I was happily and able to work, privileged really to work at Microsoft and Amazon, and kind of seeing behind the curtain of some of the decisions that get made, and absolutely those metrics and those natural disaster avoidance, floodplain avoidance, proximity to airports, proximity to large freeways. You don't want to necessarily be close to those things if you're a standalone data center. Having said that, you can mitigate some of these circumstances. So if you are in a floodplain or nearby, you can, availability zones and these parent-child relationships of data centers, have allowed for redundancy across 2, 3, 6, data centers to replicate that data, those services. And so, knowing you're going into a place where you might not have great fiber access, there was deployments that Amazon and Microsoft were doing in India, for example. It's much harder to get consistent power, fiber and uptimes where they require them in the nine nines of durability, when the power grid is unstable, like it's unstable. You don't have just plug it on and it's going to work 100% of the time. So you have to design and architect the redundancies in the system. So it costs a lot more potentially to go and do those things with the redundancy requirements and configuration. But it's all possible to architect yourself out of a paper bag if that's what you're served.
Hmm. And do some of the data centers have their own power supplies, like the ones that are close to hydroelectric facilities? Do they own those or lease those
It's
facilities?
typically leased, yeah. So it's typically leased, but it's these power purchase agreements, of large scale. It's negotiable. So they'll talk to the utility provider and say, hey, I need X amount of power or the ability to burst up to larger quantities, or I know I'm going to have double, quadruple the needs, 10x the needs over many years. And those large power agreements are multi-year agreements, and so it's a very close relationship, and a key supplier of data centers is sort of what existing power exists. If there's none there and you can't source it, that's just unviable. You can't go and build something without power. But equally, what's available and what the ability is of that utility in that county, that state, and their capabilities of producing that power. And there's so many complexities to this, David. There's not only just building the thing, you've got to then supply it. You've got to then distribute it. You've got to, there's so many things just to get power into the data center that take a lot of time, are very complex and expensive. And a good example is, in one of the examples in Europe, a data center was being built, and we were literally trenching these, to get the power from the supply to where it was needed, and the permafrost just froze over during the winter, like the land froze, and so then you kind of stuck. You can't really continue on until that either thaws out, and your project goes from a deliverable of a few months to you've just added 6 months onto that because the winter just ruined you. So yeah, there's a lot of technicalities for both power, for fiber, land, environmental concerns, and impacts when things like that happen.
I would imagine that even with those big power purchasing agreements, the data centers still have their own backup power. And then,
Absolutely, yeah.
Secondly, what role do other geographic factors like temperature and elevation and humidity play in deciding where to put a data center?
Absolutely, yeah. So there's a lot of diesel generators for backup power, and just thousands and tens and hundreds of thousands of gallons of diesel to supply that, usually all buried underground to protect them. But a lot of data centers have huge supplies up to a month or more of self-contained power to operate in the event that there's an issue. So, humidity and environmental factors absolutely play into this, and it works a couple of different ways. We talked about the environmental, the physical, things. On the environmental side, the efficiency of data centers is impacted greatly by your operating environment. For example, if you've got low humidity and high temperatures, it's easier to run using a lot of water, or not needing as much water to manage your humidity, and therefore your power usage effectiveness, or your PUE, which is a sort of an industry metric for efficiency of data center operation, varies. You might use a lot more water, but you use less power to sort of operate these things in Southeast Asia, or data centers around the equator belt. You've got high humidity to deal with as well. So you're actually running even more power to pull the humidity out of the system, because there's obviously a window of efficiency that you want to try and target. And so, you end up using a lot more power in those examples. So in other examples, and we can talk about them again later, you've got heat reuse capabilities of new and next gen cooling solutions for data centers, which is really interesting because typically air-cooled facilities, 99%, is air, maybe more. It's just dissipating that heat as condensation. It's going straight back into the atmosphere. So there's a lot of power being used, a lot of heat being produced, but there hasn't really been value on that heat because the ability to capture it's been inefficient to date. The new technologies are allowing that to be captured more efficiently, and there's some novel use cases of being able to repurpose it, which is good from a sustainability point of view.
And does humidity cause rust of the equipment inside of the data centers? And then secondly, how important is elevation? Is elevation?
Yeah, so typically not. Like, the systems are dialed in to avoid the corrosion of components from an air perspective. The HVAC units, the chillers, etc. I've not seen in a well-engineered system, let's say, kind of corrosion and things. Having said that, I've seen some pretty, I've been in the industry for 25 years, and you see some interesting things. But typically those are an anomaly, or they were not well maintained, or the system wasn't designed to operate how it's being run. And so things like dust gets into systems. This really fine silt. We had a data center in Oregon, and you're pulling in all this really dry, dusty air, and at certain points you have to manage the humidity and the temperature, and obviously that you're filtering out all the imperfections and particles from the air. And the more you filter, the more energy you use and the more power. But you were sort of managing that to a point where it was efficient, though we would get this fine silt over all of the servers, which doesn't sound that bad, but when you're pushing a lot of air around, they get trapped into different things. The interconnects not corroded, but they get dirty. And so you get light loss on optics, you get, faulty and flapping network connections. So the environmental stuff is real. I haven't done a lot personally on different altitudes and data centers that are, up in, say, Colorado and in the high altitude versus, sea level. So I can't comment on that, but there would be some interesting environmental or design choices you would make relative to, essentially it's just the thinness or thickness of the air of the inlet versus the exhaust.
Okay, is there sometimes community opposition to building data centers? Because I think sometimes they're noisy and they disturb the neighbors. When they're building all the infrastructure, sometimes that impacts local internet access, when they're digging up all the streets and so forth. And then, maybe they're a terrorist target as well. They have all that diesel sitting, on top of that diesel is all this very important data that could be literally blown up, I suppose.
Totally. There's so many, I mean, they call them NIMBYs. I don't know if you heard the acronym NIMBYs, not in my backyard. And so, there's a lot of that, and rightfully so, to be fair. These things are big, they're loud, they're not particularly pretty. Like they're these big, factories of, 4 walls and an ugly roof that are not signed. Some of the newer designs are actually kind of cool because they're trying to make them, put some green kind of tree kind of logos and stuff on them, and wooden. I've seen wooden versions as well. So it's trying to sort of dress it up sort of as a face. But you're 100% right. There's opposition. There's government regulation that's coming in because these data centers use a lot of power. In Ireland, 20%, and it could be 15 to 25% of power of the entire country is used by data centers. And so there was issues. They've got a moratorium where they're blocking some data centers that use too much power or not efficient enough. There was an example where the Irish government, I forget where it was in Ireland, but there was a dense apartment block being built for thousands of people, and this development was going to go ahead, and they worked out that there's no power to actually supply these thousands of homes and apartment blocks because the data centers are obviously using it all. There was no supply, and so there's a conundrum of, hey, do we keep fueling these data centers? And Ireland's one of the higher percentage of usages for the country relative to others. Typically, it's around 2 to 3%, but 20 is high, right? Obviously. But do you want to store, photos on the internet and cat photos, and at what point, like, there's really valuable things being done and stored versus less so, and that's being done kind of treated the same way versus folks trying to get a roof over their head, heating, and basic services. So it's challenging from that point of view, and you can see why communities can kind of push back on it.
Okay. And I guess just the last question with this issue, do they have significant security because of the flammability?
100%. So yeah, they've got, data centers here in the US, you have first responders on site 24/7. So for 2 reasons, and there's, the ability to protect those assets by virtue of weapons essentially on stock too. Secondly, they have their own, they can have their own fire first responders in there as well, because essentially if you want the fire department to come in and just hose everything down, that's just hosed, tens and hundreds of millions of dollars worth of assets, infrastructure, et cetera. So, that's not a good idea. That means, there's stringent and tight security, both getting in and getting out, and what you do in them. You get wandered down, you might get weighed walking into those facilities, into data halls, because you could walk in with a USB key, plug it into some random server, and all of a sudden that sort of bot or Trojan or worm or virus can go do things and go behind and backdoor into things. So huge security requirements for both protecting the customer data, protecting the business's assets, and everything in between. And you can imagine as well, while you're storing, say, cat photos on there, you're also doing military work. Those data centers and the workloads in public areas, well, not public areas, but in those shared facilities, are protected with their own cages and locks and biometrics and processes. So there's a lot of work that's done there, and that's a huge industry in and of itself.
So one of the, we mentioned this before, the data centers produce an enormous amount of heat, and there's a lot of technologies that are designed to dissipate that heat and, can cool the facility. So maybe just kind of give us an overview of some of the different technologies that are out there that help reduce the heat in data centers.
Yeah, so I tend to mention before advanced, next gen cooling. Typically and historically, and will continue. Air is the gold standard to manage heat. A CPU, a GPU, a device produces heat. Typically, there's a heat sink that sits on top of that. That's an aluminum or a copper type block, and then on top of that sits a fan. And that's been how we've cooled chips, both in your consumer PC and data centers, for decades. There's a few more advancements there, because what's happening is those chips are, getting more and more advanced. They're getting, smaller processing nodes and lithographies. 5 nanometers is kind of the standard at the moment, but there's even 4 and 3 happening. And what's happening is they're producing more heat. There's more power being pumped into them. Therefore, they're producing more heat. These CPUs are running at 300-400 watts each, and you have many of those in a server. GPUs are pushing 700-750 watts per chip, and you might have 8 of them in a chassis. So very quickly you're running up to 10, 20, 30, 40 kilowatts per rack, and that's not filled, right? That you would have air in between some of those rack units. So a lot of energy and effort and smart people have worked out there's a lot of different ways to sort of manage this. And so I like to think of it as sort of if you're stuck with air and you've got these AI workloads, you've got sort of 3 advancements. You've got crawling, walking, and running. Crawling, in my opinion, is sort of these rear door heat exchangers. So it's a standard rack, and you're just basically taking off the back door of the rack, moving it to the side, and then putting on this rear door heat exchange. And essentially it's a radiator. You've got fans in the back of it, you've got pipes and pumps and radiator coils, and essentially you improve the ability to cool that rack, because you're pumping fluid into that system, and it's almost like its own personal air conditioner for that particular rack. So instead of being able to do 20 kilowatts per rack, you're getting into the 30s and 40s. So you might get 50, 2x kind of capacity to do that versus just air traditionally. You're also introducing fluid at that point, right? So all of these solutions are some form of fluid. You've got a coolant distribution unit and things to manage. So all of a sudden, instead of just pushing air and not having to worry about fluid, which is kind of the kryptonite of electronics, you need to manage that very carefully and really think through the designs and leak prevention and all this type of stuff. So it progressively gets, as I go through these options, you're progressively dealing with more fluid. So that's kind of the crawling option. Having said that, the PUE, like I talked about, the power usage effectiveness of those things, is not dissimilar to air. It's slightly, it's around the same, like 1.3. So what that means is, and I'll give you the definition of that now, so we don't come back to it. But a PUE of 1.0 is pure efficiency. You're essentially not using any additional power to cool the infrastructure. You have a 100 megawatt facility, you don't use any additional power to cool it. Typical air-cooled facilities use up to 50% additional power. So again, a 100 megawatt facility would have, be actually pulling 150 megawatts to actually manage it as a total consumption. So air today fluctuates. Google's doing 1.2, PUE. Most are doing 1.4, 1.5. Around the equator, even higher, because you've got that humidity and high heat to deal with. So that could be, north of 1.5, 1.6, 1.7. The recent ones and more sustainable ones are sort of pushing that down, but there's just physics limitations of dealing with that. So a rear door heat exchange might get a PUE of about 1.3. The walk option, this direct-to-chip cooling, you're seeing it at Microsoft. They brought out their new AI silicon, their Maya chips. They've got a Sidekick, device, which is essentially a rack next to their infrastructure, which is doing direct-to-chip cooling. So that can do, circa 100 kilowatts per rack, give or take. It could push a little bit further depending on how you design it. What that means is you're essentially putting a copper plate. So you take off the heatsink and you take off the fan, and you put a copper or aluminum, cold plate sitting on top of the components producing the heat. Typically, that's the CPU and the GPU. And that heat transfers to that copper, and you've got two loops, a hot loop and a cold loop coming in. That could be a water or a glycol fluid, and you're basically just managing the heat on that copper component. And again, you're still dealing with fluid. You've got pipes and things coming in now. You've got pumps and fluids and leak prevention, and it's quite. It almost looks like you're going in to go do a stress test on your heart. You've got all these wires hanging off, and it looks a bit scary. So it's a little intimidating again when you haven't dealt with fluid in a data center. So then the run option, which is, I guess, the most interesting, but it's kind of jumping the shark a bit, and it's a bit out there, is called immersion. So essentially, think of a bathtub full of fluid. In most examples, it's a dielectric fluid that's non-conductive, non-corrosive, and you essentially bathe the servers in that fluid. You dunk them in. They're not rack mounted vertically. They're literally sitting, face down in this fluid. But the advantage there is not just the CPU and not just the GPU, but all components get the same heat rejection because they're encased in the fluid. It's 1,000 times more efficient than using air. And so what happens there is that fluid is pumped, through those tanks. It hits a heat exchange, and then there's a second loop that comes in the other side of the heat exchange that then just goes out to evaporative cooling towers, dry coolers, or chilled water loops. And so there's a second. There's two versions of that. There's a single phase, which I just described, and then there's a two phase, a little bit more advanced, but uses it basically boils off the fluid and the condensation drips down. A lot more complex, but the industry seems to be kind of agreeing that single phase is probably the most efficient and convenient, although you're dealing with a bathtub of fluid, way of going about it.
So there's another term, cold plate cooling. I'm not sure if you discussed that, but maybe just define what that is if you want.
Yeah. So the cold plate is essentially that direct-to-chip cooling. So that walk option I was kind of talking about. So that is a copper cold plate. It literally sits on. It's machined out, and this is the challenge I find with it, is because you can think about how many servers you have. You have racks. You have HP, Dell, Supermicro, Gigabyte, whoever. Every single motherboard looks different. And so if you've got to think about, if you don't use one vendor and one SKU and everything else, which no one uses one vendor and one SKU and only these things, because it's just, especially at the moment with supply, everyone's buying whatever they can buy from whoever's got it. But if you're trying to ensure that you've got a design for every thing in a rack or in a row, you're going to have a lot of different SKUs of cold plates as well. And it's not as simple as just bolting on, a heat sink and fan that you've typically been able to do and get one manufacturer to do it, because you're dealing with essentially a square. These things are, off center, and one's over here, one's over there. And so it becomes a little more challenging to do that. But it's essentially, that's the copper plate that you're referring to is the direct-to-chip cooling. Those have got good PUEs, that they're sort of, 1.05, 1.1. Sort of that's as good as immersion. Immersion circa 1.05 as well. So again, using 5% power to cool that versus up to 50 and beyond for air. So these are really good use cases, especially with the AI chips for using a lot more power. These advanced cooling methods are becoming more standard. Direct chip cooling now is essentially mainstream. You go to conferences, they're everywhere. Immersion, I think this year will get some more runs on the board and be more commercially available. But as you can imagine, the challenge there is the OEMs, the vendors, the Gigabytes, Supermicros, Dells, etc., have to not only warranty the servers and the power supplies and everything that breaks and needs to be replaced. Now they're dripping in fluid. I mean, that's different to just being shipped back in air. But the second piece is the components they use. So you're thinking about higher heat, temperatures in those environments, and it's now covered in this fluid, and that fluid will just start, damaging or the materials start deteriorating and labels peel off, and there's all these little bits where certain types of plastics respond to under different temperatures and environmental conditions. So there's a large piece of work that needs to be done and is continuing to be worked on in that space to make that more or more desirable and less painful.
Are the chip companies trying to make their chips less heat generating?
Not really.
Okay. Right.
Not really. And so, well, yes and no. So the heat is a byproduct of performance and things. So when you go down through different processing lithographies and the different nodes you hear about, so you hear about Intel 7 and TSMC's 5 nanometer process. Your iPhone is on the brand new ones are on a 3 nanometer process that they produce. And so as you shrink those nodes, you typically either do one of two things. You obviously reduce the power utilization at the same. If you'd produced it on 5 versus a 3 and you did nothing else, your power usage would drop. Sometimes you get both. Sometimes you get a power drop and a performance gain because you free up more space on the chip to add more capacity, more cores, more CUDA cores, more neural networks, whatever, decoder blocks. And so that allows you to do one of two things. And what's typically happened though is, as those nodes have shrunken, NVIDIA, Intel, AMD add more cores, add more performance. AMD's embedding the memory onto the die as well now, like onto the same chip, and bringing it closer for performance and lower latency. So you're seeing power draws increase. So as I talked about, the Intel chips are now pushing 400 watts. They never used to be 400 watts. They were circa 100, 200, and then they just sort of went woof. Recently, NVIDIA's H100 is 700 watts. AMD's MI300X is 750 watts. NVIDIA's Superchip, which is their ARM processor and their GPU, their GH200 they call it, that's a kilowatt, right? And so it just keeps going up. The future chips are going to be even higher. NVIDIA's talking about liquid cooling as an option to buy it from the manufacturer. So there's an absolute, maybe it's not, I wouldn't call it a dirty secret, but it's a known quantity that this is a huge problem. And those nodes are going to get to a point where there's going to be a law of diminishing returns. I mean, they talk about Moore's law, sort of going away to some degree, because those shrinkages are getting to a point where you just can't shrink using silicon anymore, and there'll be a new advanced kind of replacements like graphene and others instead of using silicon in the future. So to continue that journey of 2 times performance every 1, 2, 3 years.
So there's a lot of new technologies you mentioned. What is the appetite of data centers to embrace new technologies? On the one hand, they offer promise of better cooling, less power consumption, more efficiency, and so forth. But on the other hand, the tolerance for downtime is practically zero, right? And performance has to be just about 100%. So
You might be surprised. So that's true, and that's true across almost every use case. But with AI, the tolerances for 100% uptime, it depends on that's a different use case. And so because a lot of companies are using, proof of concepts, and they're kind of, testing and playing and prototyping with AI, the requirement for it to be up 100% of the time is just not there. And you can imagine creating redundancy for, like, these systems are hundreds of thousands of dollars for, the entry level systems. A chip from NVIDIA is 40 grand. Their latest, the AN H100 chips, 30, 40 grand. And so that's a lot of money and you're getting 8 of them in a chassis, RAM, CPU, all that stuff, and then cooling and powering the thing. So, it's the redundancy, and then you got to put a network on top of that, by the way. InfiniBand also ain't cheap. So it gets very expensive to have redundancy through those systems. So, you can, like I was talking about before, with architecting your way with redundancy from a physical point of view with data centers. Some companies are sort of, toying with that idea of saying, well, how redundant do I need this to be? And what's it going to cost me? And what's the sort of cost benefit analysis of it? And there's some interesting answers, especially on the AI side, at least as it starts off. But to your point, for core critical services that we've all become accustomed to being never down, 100% needs to be as many nines in the percentage as possible. The more nines, the better. But I would say AI is kind of, at least at the moment, pushing back on that somewhat. What was your other question there, David? I kind of skipped over the first half of that. I'm sorry.
I suppose maybe for the existing data centers, they may just want to stay with their existing technology. They've already
That's right. I'm sorry.
A lot of money there, but maybe the newer facilities may be more willing to test new technology.
Yeah. So like I mentioned with those advanced cooling technologies, so there's obviously a lot of different ways to think about it. There's build, so you own and operate the data center. So data center operators, Equinix, Global Switch, etc. And then you've got the hyperscalers that are obviously building their own and co-loing with those kind of vendors. So if you're selling white space as a service, and you've been selling air essentially as a service for decades, it's a hard concept to think about changing that model, because it's been quite good, for those operators, who have been providing that as a service. And so most of the things I was talking about, the rear door heat exchangers, the direct chip cooling, and the immersion, is still relatively in its infancy. However, AI has accelerated the need for these things. So I guess the point I would make is most large scale data centers have taken a wait and see approach to some of these things. But some of them have actually started this process. There's news that companies are doing direct chip cooling and offering that as a solution. So therefore, I will, if I'm a data center provider, I will plumb water or fluid to your rack location now, because if you're gonna bring in a rack and want to do 50 kilowatts in that environment, I expect you to be using. I can't cool it with air if I'm an air cooled facility. So I expect you to use advanced cooling techniques. So I have to plumb fluid to your location now, not just to my own chillers and HVAC units and things. So they have to. That's a cost, and that position is now more expensive as a result. Some of them are doing, like to your point, greenfield environments. So new builds have the optionality. So they're already being built with those things in mind. Doing higher heat loads in some areas and distributing it around so you don't hotspot. And I've seen brownfield environments with immersion data center tanks sitting next to air-cooled racks. And so, I mean, the challenge there is you're actually buying 2 or more positions, because you're talking horizontal versus vertical. And so unless you can stack them, which is really difficult to do, and trying to pull the things out of fluid with cranes and cranks and things, winches, you just have a physical challenge there with regards to logistics, and then leakages and fluid and dripping. You got to let the thing drip out before you move it. So Yeah, it's existing data center companies have been, I would say, larger ones are slower to react. Not unsurprising, but then you're seeing a lot of smaller data center operators and brand new ones creating these bespoke and edge type deployments where you can go and get a megawatt of capacity in a shipping container and plop it wherever you need it, and it avoids that issue we talked about before, which is it's quiet. An immersion tank doesn't have any fans on it. You take all the fans off the power supplies, the GPU, the CPU, all of it, and so that reduces your power usage for starters. But equally, it reduces the noise it makes. It doesn't make any noise other than pulling in ambient temperature from outside or running a small air conditioner for the poor person who's sitting in there operating on it. So just to make it a bit more human friendly. So it's it's coming from the bottom up, I think, in those smaller instances from edge and micro deployments. And and I think we'll talk about a bit later. The proximity of these things aren't in off the Columbia River. It's getting closer to the user where the use case is most needed.
So if I had a new cooling technology, what criteria would the technology be evaluated on by the data centers if they're considering procuring it? It would be the
Oh,
cost,
good question.
power consumption, reliability, warranties, maybe maintenance.
All of the above. I think one of the things that I've run into with so you've got data center operators, and then you have data center operators. So the folks that are stare at the staring at the racks, they do the break fix, cabling, rack stack patch. So the resistance from folks typically in that operation environment are they've become very good and efficient at these facilities. Pull out the rack, re-rack it, change the DIMMs and the power supplies, and then throw it back in. And all the telemetry, all the systems, all the operations are all tailored. Even the automations are tailored for that environment. So they've built a very good and mature system that these new techniques blow out of the water. You need new telemetry, new metrics, new observability tooling that doesn't either exist or it's very immature. And so also connectivity to BMS. So you need to know what the building management system is doing, the environmental, the pumps, the pressures, the temperatures, the outside temperature. There's just a lot more to think about that can go wrong, rather than things that we've seen. Most things that can go wrong in an air-cooled environment, having seen it for decades. So it's the unknown versus the known. So there's resistance there. But to your point, it's power usage. It's how much of a pain in the butt is it? Like I just talked about, that there's a lot of resistance to that, especially at the folks, on the in the weeds. And then to your point, it's warranties, being able to, what happens when something breaks? What happens? And so on top of that, I think just, things like not only where it breaks on the system that is cooling, but it's the actual system itself. So what sort of self-healing capabilities are there? For example, if you're using immersion cooling, you might have a failure of your heat exchange. And so, you've got this tank, which is, expecting to mitigate all this all this heat. And, the pump stops. Well, what happens? Well, very slowly, and it's luckily very slowly, the fluid will rise, and there's inertia in that fluid. Typically, an air-cooled facility, if the air conditioners break, those things will rise temperatures almost immediately, right? Because there's just the resistance there's no inertia in the air. And so you're going to start the air temperature of the ambient air temperature will sort of rise, and then the chips will just keep going. With the fluid, you have a longer time to failure once there is a failure upstream. But equally, you'll have a slower time to restore or bring that temperature back to its normal limit because of the inertia in the fluid. So all that type of stuff needs to be documented, thought of, and that's why operators are kind of resistant, because it is a real change. It's very different to what they used to.
Okay, and then hit a couple more things pretty quickly. I hear that there's some efforts to divert the heat to other applications, to heat swimming pools, and I'm not sure if this has been implemented yet, but to heat low-income housing in
Yep.
that kind of thing?
Yeah, so this is really important in cold climates because you can, the heat is more valuable than in high heat climates. But it's a good sustainability win. What I think is interesting about it, I think I it's a very it goes to the circular economy and the circular kind of environment that data centers want to be involved in, the sustainability front. And these new methods of cooling allow higher efficiencies, heat capture on the other side, especially immersion. It's almost 95% of it can be pulled off and then used in a commercial laundry or a swimming pool or a spa or something. There's a great advocate of this, Mark Bjornsgaard of Deep Green Tech. He's based in Europe, and so he's a good person to follow on this stuff. There's also another group within OCP. So there's Open Compute Project, which is a global initiative that many large companies, Meta, Microsoft, and others are sort of into, that are trying to make this more of a thing and trying to get more attention to it. And I think it's a great sustainability focus, though I think to your point, the use cases have been somewhat novel. But I would love to see, and I think it's you can design this easily. You can put these immersion data center tanks on the top of it, to your point, residential block of thousands of apartments and essentially heat them for free, or pump it into district heating or some version of where that heat is valuable. Because again, if you've got that, noiseless or environment, and you're producing the heat, you may as well do something with it, and that's a great use case. But I haven't seen it used at scale or used in any material, large scale deployment, other than I think there's a couple of swimming pools. There's some one of the guys out in Wyoming, Trenton Thornock, is using the heat that they're producing in their data centers to essentially build a greenhouse. So I think the metrics are, and he's very, correct me if I'm wrong, but I think it's like every 1 megawatt gives them 1 hectare or 1 acre of greenhouse capability. So what they're doing, which is great, is instead of shipping all their fresh fruit and vegetables in from California, they can produce it locally in Wyoming, saving 1 to 2 days of travel time, the diesel it takes those trucks to get over there. So those type of things I think will move the needle, and that's material impact that's for the greater good.
Okay. And then are almost all new data centers being built with sustainability in mind? Do they have to comply with certain sustainability standards, or is that more optional in return for becoming sustainable? Are there tax incentives and tax credits, that kind of thing?
Yeah, good question. So it and it depends. So depending on, in Europe, for example, it's very difficult to go build a data center without having to, show behind the curtain about what you're doing and what you intend to do, et cetera. Just with the regulation there. Same goes in Singapore. I mean, Singapore had a moratorium which essentially said, unless you had a PUE below 1.2, I think it's 1.2, no, you can't build a data center with us. I mean, obviously, it's small country, small landmass, or small landmass. The ability to go build data centers which use a lot of land, use a lot of power, on an area that doesn't have the ability to do that at many more. You've got a lot of multi-story data centers in Singapore as an example, but they just don't want to use the flat surface. You aren't able to get access to the power. You aren't able to get access permits to the land. Everything just stops. So those things are real. The example I gave for Ireland before as well, and it's happening in Germany, I think, as well. So that's all real. I think the regulation as it relates to other metrics hasn't come yet. So you can play with PUE essentially. You can just throw a lot of water in the system, burn gallons and gallons and gallons of water, and bring your PUE down, but you're just burning through drinking water. there's some metrics that you could use. You could play with it even more and say, well, I'm using water, but I'm using brown water versus drinking water, right? So then that's less bad. I mean, but then you're going to be measured the same way. Again, OCP that I mentioned before, a shout out to those guys, because there's a whole subgroup of people working on different metrics and how to measure things more accurately and reliably, because PUE has been the gold standard for a very long time, and it's hackable / you can you can cook the books, so to speak, if you really want to. And there's things called partial PUE, there's a WUE for water, there's a whole lot of other different metrics that go into it that I think that will be really helpful when regulation and sustainability requirements come in, and they will, to sort of have better standards, because the current one just doesn't serve its purpose very well.
Okay. And then how big of a factor do you think quantum computing will be on demand for data?
Yeah, good. I must say, whilst I'm a believer in quantum, I'm not an expert in it, and by any way, shape, or form. Many are. It hasn't been something I've been interested from afar, but my standard response is it's always been 5 years out, and it has the capability to do some incredible things and high expectations. I don't know if we've seen much by virtue of realizing those impacts just yet. So, but I it's hard to say. I'm just not I'm a believer, but I'm just not close enough to the details to give you a good response on that one.
Okay. And then how do data centers price their services? Is it per megawatt or?
Yeah, so well, data center services relating to customers are just pricing it for the services they provide. Are you talking about the utility providers to data centers? You're talking about, so like so just could
Yeah,
you?
if I'm a customer, I guess. So it's part of the
Oh,
cloud.
I see. If I'm colo, so yeah, so all right. So a data center provider, I'm thinking hyperscaler. Sorry, I just would narrowly focus there. So if you are wanting to put infrastructure in a colo, in a co-location, data center, you are typically offered, a square footage. So like it's rack space. So I've got a tile for your racks, and certain footprint. Cost a certain square footage cost. They'll typically then add the power costs for your usage, and there's variation to those things. It's typically a pass through, so whatever the utility is charging them. So let's say it's 10 cents per hour, then you're going to just keep passed that through of how much you're using in your rack relative to the time you used it. There's some variation to kind of caps and peaks and those things, like at a 90th percentile, but for the most part, it's pass through. You might then have some costs on, or you will have some costs on cross connects. So you got a network that you have in that environment, and if you're linking into other, networks, like you want to cross connect into AWS or Azure or, Cloudflare, or whoever you're using or whoever you're peering with and connecting to over IP transit, you'll have cross connect costs both as a one-off to connect, and then an ongoing that you kind of have into their network, because you're essentially using a network port on their switch or router. So you have to essentially pay for that privilege. And if you want to, the colo might offer you, IP transit themselves. So you might pay additional costs for bandwidth of traffic. You might leverage their WAN, and you might go out and buy, terabytes of capacity, or gigabytes of speed in and out as an egress and ingress for network. But those are the typical things that you would pay for. Just the physical location, the power to supply it, and then the connectivity out.
Okay. And then last question, any interesting elements that would be in an equipment contract? So if I have a new piece of equipment that I want to sell to a data center, any contractual issues I maybe should be aware of?
Uh, nothing out of the ordinary. I think, it really depends on what goes in. Like if you're talking about, IT equipment that's going into the data halls, it's the HVAC system that's going to be environmental. It could be internal, external to the facility. It could be, you could be offering services like I talked about the security service, right? So like it really depends on what is the product or service that you're selling them, but nothing too dissimilar to, not really, would be my
Okay.
answer.
Okay. Great. Well, Nick, thank you so much for spending all this time with us and answering all these questions. We've covered a lot of ground in this almost hour. So really appreciate your time and your expertise.
David, thank you for your time as well, and always love talking about this stuff. So, part two, we can get into it even deeper if you're happy to do that at a later date. But yeah, pleasure talking to you, and thanks for your time.
Sure. And if you want to, you can tell people how to contact you or your website address.
Yeah, so humeconsulting.co, is the main portal. LinkedIn, I'm Nick Hume on LinkedIn. I've got a little newsletter that I put out bi-monthly, so every 2 weeks, called Infrastructure as a Newsletter. So you can subscribe to that. I haven't got as big a following on Twitter, but I'm growing that too. So my handle there is Cool Kids Do It, which I sort of use a lot of things on LinkedIn go on there as well. So lots of different ways to sort of follow what I kind of post and write about, and a lot of the areas we covered today, and more. So yeah, otherwise just my email address is on my website too. So hit me up that way.